Okay, so continuing here our discussion of enthalpy, right? And what we're looking at now is the third type of enthalpy problem we were talking about, and we should probably focus just for a minute on making sure we can recognize that problem. So enthalpies of formation, right, go along with each individual molecule or compound that is in a reaction. And if we want to calculate the enthalpy for that reaction, we can use our equation that sums up the enthalpy of formations of the products and the sums of the enthalpies of formation of the reactants and combines them together, right? Combines is probably not the right word because it's a subtraction in there, but like puts them in the appropriate place in the equation. So what you would see in a problem is possibly something like this. So in the problem that I have here, the example, I've actually looked these values up in a table in the back of a textbook already. So really on a test, right, you're not going to have access to your textbook. You're not going to be able to look things up in a table. So on an exam, the problem should look something like this. You'll be given all of the enthalpies of formation that you need for that reaction, right? And then what you really need to do is be familiar with the formula and be able to apply the formula correctly. Now, it is important to recognize if you're doing problems in the textbook, practicing problems, there is a table in the textbook, so you may not see all the data here. You may just see the equation and be asked to calculate what the enthalpy for the reaction is. If that's the case, you can go to the appendix in the back of the book and look up those values. Thought I was going to sneeze there, but lost it. But you can go to the appendix and look up all those values if necessary to solve the problem. So keep that in mind. You won't always see them, right? But you can still use them to calculate the enthalpy for the overall reaction. Okay, so there's a little bit of lead in here about the problem. So it says Romans used calcium oxide to produce a strong mortar to build stone structures. Calcium oxide was mixed with water to give calcium hydroxide. That's what we have here in our reaction. Calcium hydroxide then reacts with CO2 and forms calcium carbonate. So we've got our calcium hydroxide reacting with 1 mole of CO2. We get calcium carbonate. We get some water, and the water is going to evaporate away here in this process. Now, it's 1 mole for every component of the equation, right? And we'll have to factor that into our calculation, but that's something I'll kind of point out as we go along, and I'll explain how it would be different if there was a non-1 coefficient in a reaction. I'm going to calculate the standard enthalpy change for the reaction. So what we're going to use here is the formula that was introduced in the last video, and that is the change of enthalpy for the reaction, and these are standard, so you'd have the little degree sign, is equal to the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. So if we have all of those values, we really just need to combine them in the right way, or fit them into this equation in the right way. Again, it's not a combine, it's a subtract here. So we're combining them in each of the sums, but then we're subtracting for those sums. Okay, so that's what I'm going to do. Sum of the products, that would be each of these values for the products. So I've got the value for calcium carbonate, and what I'm going to do is I'm going to put a 1 in here because we know enthalpy is related to moles of material. So this enthalpy of formation is for forming 1 mole of a particular material. If the coefficient is more than 1, that will have to show up in our calculation. So I'm going to add these 1s in here just for clarity for when you're doing a problem where those values aren't 1. But 1 mole of calcium carbonate times its enthalpy value. So 1,000 negative 1,207.6 kilojoules. I'm summing, so I'm going to add the other product. There's 1 mole of water, and its enthalpy is enthalpy of formation is minus 241.8 kilojoules. Okay, so square brackets there to finish off sum of the products. I'm going to subtract the sum of all the reactants. Now they're both 1 mole as well, so 1 mole of calcium hydroxide minus 986.1 kilojoules. And summing here, so I'm going to add 1 mole of carbon dioxide which is minus 393.5 kilojoules. And that would be the end of those square brackets, so the end of that summation. Now, if I combine inside each of the square brackets, I do that on my calculator here. So those are both negative. I'm going to enter them in as positives, but then carry the negative down. So the sum there would be negative 1,449.4 kilojoules. And I want to subtract the sum in the second set of square brackets. So 986.1, 393.5. And in that set of brackets would be minus 1,379.6. And again, that's kilojoules. Right now, watch here, we're subtracting a negative. So factor that in. If you get two negatives together like that, do that math, and this comes out to be minus 69.8 kilojoules. So the enthalpy for this overall reaction, and it is standard, so a little sign there is reasonable as well, would be minus 69.8 kilojoules. Okay, so I don't think these are particularly complicated as far as problems go. You do have to remember your equation, and you also have to recognize the type of problem. If you see this problem and you start trying to work it like either a Hess's law problem or a dimensional analysis problem, it's not going to work out because you just don't have that set of information. So again, I think if you're thinking about, oh, what type of problem am I about to tackle, that will help a lot in making sure that you know what to do when you get into that problem. Now, the second problem here, I think, is an interesting thing. This could be part A and this could be part B of the same problem. Once you've solved either a Hess's law problem or an enthalpies of formation problem, you now have the same set of information that we described as being the first type of enthalpy problem. We've got a balanced equation with an enthalpy. We just identified the enthalpy of this reaction. So it will not be uncommon that part A would be Hess's law or a enthalpies of formation problem, and then part B will be that first type of problem that's really dimensional analysis. So part B here says how much energy as heat is evolved or absorbed. So that is worded that way so aren't given it doesn't give away what the sign is here. This is a negative. That means this is an exothermic reaction. So that means heat is being evolved here, not absorbed. So we could simplify that. How much heat is evolved if 1 kilogram of calcium hydroxide reacts with a stoichiometric amount of CO2. So 1 kilogram of the calcium hydroxide. And since this is the first type of enthalpy problem, right, we have a balanced equation, we've got its enthalpy, and now we're relating energy to some quantity. Right? This is unit conversion. So from kilogram of calcium hydroxide, we want to work our way to energy. So let's go to grams first. There'd be 1,000 grams in a kilogram. Right? And then from grams of calcium hydroxide, we can go to moles using the molar mass. So 1 mole of calcium hydroxide. Right, and we'll need to figure out how much does that weigh to cancel out our gram units. So 1 calcium, 2 oxygens, 2 hydrogens. Calcium is, periodic table handy, 40.08. Right, we've seen oxygen quite a bit. It's 16, so 2 of them is 32. And hydrogen is 1.01, so 2 would be 2.02. So that would be 74.10. So 1 mole of calcium hydroxide is 74.10 grams of calcium hydroxide. And remember here, the enthalpy is per mole. So that's how much energy would be released per mole of calcium hydroxide, since there's 1 mole of calcium hydroxide in that balanced equation. So 69.8 kilojoules per 1 mole. And again, we don't carry that negative. That negative is helping us understand whether it's exothermic or endothermic, right? That's what determines which of the two terms applies to the reaction. But once we've identified which it is, we're still looking for a positive number down here because the reaction is either absorbing heat or releasing heat. You don't really want to say absorbed a negative amount. That's kind of like saying, well, I lost -2 apples instead of I have 2 apples, or I gained 2 apples. So it would kind of be using a double negative. So units work out here to heat, so we just need to punch this in. So 1000 divided by 74.1 times 69.8. And we have a 3 significant figure limit here, so 942 kilojoules would be the amount of heat given off by that reacting that much calcium hydroxide. Okay, so one more page here in the chapter. We will cover that in one more video, but we'll take a break right there.